Good. Okay. Hello, everybody, and welcome to our second lecture in the data analysis part of the Biostatistics CTR seminar series. My name is Jess Kaminsky. I am a second-year master's student studying biostatistics. I just want to give I just wanted to give a note to the people on Zoom that there is a handout. You should check your email for it. If you don't have it, you can send a message into the chat, and Allison Green will help you out with that. Okay, so what are we going to go over today? We're going to go over some simple examples and some other examples that I hope motivate the study of probability and also demonstrate that sometimes probability theory isn't as intuitive as you might hope it is. We're going to go over the language of probability, so how do we speak about probability? We're going to go over probability notation, so how do we write about probability? We're going to go over some formulas and theorems, which are mostly listed on your handout, and then some examples. So initially, why do we want to learn about probability? So this is the data analysis section, and learning probability is essential to us understanding randomness and us also understanding statistics and data analysis. So let's start with the most basic example, just tossing a fair coin. What is the probability of getting heads? You probably know that it's 1/2, but let's go into how you figure that out. So whenever you're asking about any probability, you want to answer two questions. One, how many unique, equally likely outcomes are there? And two, how many of those outcomes contain your outcome of interest? So when we are tossing a fair coin, we know that two things can happen as long as something crazy doesn't happen and it lands on its side. And a fair coin meaning that the probability of it landing on one side or another is equally likely. Sorry, that's okay. Just looked very funny on camera. So two things can happen. How many unique, equally likely outcomes are there? Two. It's heads or tails. And because our question is, what is the probability of getting heads? The number of outcomes that contain our outcome or event of interest is 1, heads. So the formula, the most basic formula for the probability of an event is the number of ways that that event that you're interested in can occur, divided by the number of total possible outcomes. So in this case, it is 1/2, or 1/2. Let's extend that a little bit further. Keeping in mind this formula, I want to first also introduce you to some probability notation. This P, parentheses, rolling a 2 or a 5, that's how we write the probability of rolling a 2 or a 5 if we're rolling a fair die. So when we're rolling a fair die, we know that there's 6 total possible outcomes. So any probability that we write about the outcomes of rolling a fair die, the denominator, that number on the bottom, is going to be 6. And the number on top is going to pertain to whatever we are interested in. So if we're interested in rolling a 2 or a 5, there's 2 ways that outcome can be satisfied. We roll a 2 or we roll a 5. So that's 2 out of 6. Also, if we want to talk about the probability of rolling a 2 and a 5, that probability is going to be 0 because there's no way to possibly satisfy that if we just roll the dice 1 time. Okay. I want to introduce you to the Monty Hall problem. I'm going to present it here and sort of just explain the results of it. And then at the very end, we're going to use the formulas that we learned throughout the course of this talk to derive the same answer. So this problem is you are on a game show and there are 3 doors. There's a prize behind one door and there's nothing behind the other 2 doors. And you are given the opportunity to choose one door. After you choose that door, the game show host is going to open an empty door and show you that there's no prize. You will then have the opportunity to keep the door that you have chosen or switch a door. Then the door that you end up with will be opened and you either win or you do not win. So do you think that it doesn't matter, the probability of switching, the probability of winning does not matter if you switch, or if you switch or keep your door? So out of my audience, do you think switching the door will increase your odds of winning? Keeping your door will increase your odds of winning? Or do you think it doesn't matter if you switch or keep your door? So raise your hand for it doesn't matter. Raise your hand for switching. Switching? Raise your hand for not switching. Not sure. Okay, so in the audience we had one member say that switching would increase your odds. So that is correct. Switching actually will increase your odds of winning. So you have 3 scenarios. In each scenario, we're going to say that your choice is door 1. Now, there's 3 ways that the prizes can be laid out. The prize can be in the first door, the prize can be in the second door, or the prize can be in the third door. In scenario 1, if you chose door 1, the host will show you door 2 or 3, but either way, you should not switch if you would like to win. Similarly, in scenarios 2 and 3, you have still chosen door 1, which does not contain the prize. And in both of these scenarios, you're going to be shown the door that does not have the prize, and it's going to be beneficial to you to switch to the door with the prize. So, looking sort of at probability, the probability of switching and winning is 2 out of 3. 2 of those scenarios will cause you to win out of a total of 3 possible scenarios. Okay, so now I'm going to introduce to you some different language of probability and go over how we speak about probability. An event is the basic element in probability. It is the result of an observation or an experiment. So the experiment in the simple examples would be that one coin toss or that one roll of the dice. The event is something that you can definitively say occurs or does not occur. So some examples that we're going to use moving forward. Event A is the event that a mouse lives to age 3. That can or cannot happen, and you can definitively say that. And event B is that the event that the mouse gets skin cancer at age 2. Again, something that you can definitively say does or does not happen. Sets. So a set is a collection of distinct elements, symbols, numbers. Whenever we write out sets, we write them in curly brackets and we list all of the distinct elements that are in it. So red, blue, green, 1, 3, 5, 11 are all sets. If we let A denote a set, these notations right here, this A and then this curly E, capital A means little a is an element of big A. So if we look at this red, blue, green set and we called this set A, we could say red is an element of this set A. And then the same notation, but with a line through the symbol, means that that little a element is not within your set A. If every element of a set is also in set B, then that set A is a subset of B. So say that set B is all the colors of the rainbow, red, orange, yellow, green, blue, purple, and set A is red, orange, yellow. You can say that set A is a subset of set B. Okay, so the set of all possible outcomes is called your sample space. It's often denoted by the omega or sometimes a capital S. So in our dice rolling scenario, omega is the numbers 1 to 6. In our coin toss scenario, omega is heads or tails. Another example, subsets of sample spaces are called events. So each of those, so in example 1, events 1, 2, 3, 4, 5, and 6 are the 6 individual events that could happen from this one experiment of rolling a die. Another example, so you're driving to work and you go through 3 intersections. At each intersection, you either stop or continue. So your sample space is the, or the 8 different combinations of stopping or continuing that could happen at each of these 3 intersections. Another example, during the next year, you have a certain number of visits to the doctor. So this sample space is actually, it starts at 1, and it's every number up really to infinity. I mean, it's not going to be up to infinity because that's not a realistic number of visits, but this is a string of continuous numbers. An example 4, the empty set. This is denoted with this 0 with the slash through it, and we will go through some examples of when the empty set comes up in set theory and probability. Some general properties of probability. Every event in your sample space is assigned a probability. Sometimes they're not equally likely. So in the coin toss and dice rolling, each of those events have an equal probability, half and half for heads or tails, and 1/6 for each of the die rolls. But sometimes we get unequal probabilities. However, the probability of all the events in a sample space, so right here we have P of omega, the probability of all the events in the sample space, always needs to add up to 1. Whatever we're doing, all the events, we need to be able to guarantee that at least one of them is going to occur. Given that A and B are events, the probabilities of these events are always between 0 and 1, or between 1 and 100%. Okay, so some language of probabilities and some set notation. The union of A and B is the set of all things which are elements of either A or B, and it's denoted A, U, B. And we'll go over all of these in more detail on later slides. The intersection of A and B is the set of all things which are elements of both A and B. So union was like that example before when I said I believe it was a 2 or a 5. That was looking at the probability of a union of 2 events. Intersection of the probability of rolling a 2 and a 5. That was looking at the probability of an intersection of 2 events. The complement is the set of all elements which are members of the sample set space, but not members of A, and we denote that A, C. So more about the intersection. So if we look at a Venn diagram, this is sort of how we denote Venn diagrams. The big square in this omega shows us that this is our entire sample space. Things can happen inside of A, things can happen inside of B, things can also happen outside of A or B. But any possible event within our experiment will happen within this bound. So A intersection B, right, that's where these 2 circles cross. And going back to our previous example of A and B, A intersect B is the event that the mouse gets cancer at age 2 and lives till 3. So any event that satisfies both of those will fall into here. Okay, so I'm going to start throwing some formulas at you. Some of these are going to be less intuitive than others and don't necessarily have a great way for me to fully explain them. So for some of these, just bear with me, and then I hope that the examples later on will make it a little bit more clear. Yes? Mm-hmm. So if you had a dice roll, you would have 1 through 6. That's a sample space. Mm-hmm. Yes, yes. So for that notation, I think you would just write it. I don't really know if there's a way. I guess you would write 1, 2, and then that C subs. Let's go back to here. This. Mm-hmm. Okay. So you're asking, how do you use set notation to write an intersection or a union? I don't know if I have a clear answer for that, but if it comes to me, I will let you know. Thank you. Okay, so this formula, we're looking at calculating probability of an intersection. So calculating the probability that events A and B occur. So we can use probability of A times this conditional probability, which is the probability of B given A. So this, we'll do more with conditional probabilities later on, but this is the probability that B happens given that you already know that A happens. Okay? If you don't have this information, you can also calculate the same probability of this intersection using the second formula, the probability of B times the probability that A has happened given B has happened. If A and B are independent, then we can use this formula. What independence means is that the probability of B occurring does not depend on whether or not A has occurred. So we can just use these. Basically what happens is, if we're using this top formula here, and we come down here and say that A and B are independent, what's really going on is we're saying that the probability of B given A has happened is really just the probability of B, because it doesn't matter whether or not A has happened. So as I said, independence means the probability of B or A does not depend on whether or not event A or B has happened. So we have this result here, which I just explained. So in a coin toss, right, if you toss a coin once, the result of that coin toss has absolutely no bearing on what the next coin toss is going to be. So we can calculate the probability of A getting a heads on the first toss and B getting tails on the second toss as 1/2 times 1/2, because those are their individual probabilities, and the result of one does not affect the other. So a union, as we said, this is or, the probability that A or B happens, probability that the mouse gets cancer at age 2 or lives to 3. So it's anything that falls in either of these circles. Okay. So calculating this probability, I think, is a little bit more intuitive than the intersection. So the probability of A union B right here is equal to the probability that A happens plus the probability that B happens minus their intersection. The reason that you're subtracting out that intersection at the end is because you added it in once right here, but you also added it in a second time here. So you just need to take out one of those in order to get an accurate representation of this space here. Okay, so complement. So this is everything that's not A. So I think sometimes people get confused about the space outside of the circles, but as I said, this is still included in your sample space. It is just things that are not defined by event A or event B. So A complement is the event that is not A. So if we want to calculate the probability of A complement, that is the probability of your sample space, everything, minus the probability of A. Now we know that the probability of your sample space is 1. And then we just subtract the probability of A from that. So mutually exclusive events, this is a little bit different than independence, and I think sometimes they get confused. So if A and B are mutually exclusive, this is also called disjoint. That means that they cannot occur at the same time. They cannot both occur, only one can happen. So this is the intersection of A and B is the empty set. There's nothing that can happen for both of them to happen. So this is rolling a 2 and a 5 at the same time. It's not possible. So probability of mutually exclusive events. The probability of their intersection is 0. Only one can occur. However, their probability of their union is just the sum of the two probabilities of these events. And in this case, we don't have to subtract off that intersection because it's not getting added twice because there is no overlap. And then we can apply the same reasoning to multiple mutually exclusive events. So if you have 3 events, there's no overlap among them. The probability of all of them is just the sum of their individual probabilities. Okay, conditional probability. So we saw this a little bit. The probability of A given B is a conditional probability that event A will occur given that event B has already occurred. And this is a little bit different than just the probability of A. So what this conditional probability is saying, so let's talk about this one. Probability of A1 given B. There's some probability of falling into this circle B, right? And then we know, we already have the information that we've fallen into this circle B. Now that we know that, what is the probability of falling within this smaller subset of B, A1? Which is also different from just the probability of A1, because A1 includes all this extraneous information that is not relevant for this conditional probability. So given that your probability of B is 0, given that you have some space B, the probability of falling into A1 given B is the probability of their intersection, so the probability of this space, divided by the probability of B, the probability of this whole space here. So in practice, I wanted to give you an example of when we might be interested in a conditional probability. So if H plus and minus is HIV status positive and negative, and T plus and minus are a diagnostic test for HIV that the results can be positive or negative. This we read as the probability of HIV testing positive given the test is positive. So what is the probability that your patient actually does have HIV given that their test status was positive? This here should be a negative, and this word should say negative. So probability that HIV is positive given test status is negative. What is the probability that your patient is HIV positive given that their test was negative? Okay, next is the law of total probability. So given you have events B1, B2, all the way up to Bn, any number of B events are disjoint and exhaustive. So disjoint, we went over, means mutually exclusive, means there's no overlap between these events. What exhaustive means is they take up the whole sample space. So this shows you that B1 to Bn are disjoint, no overlap, and exhaustive. They cover that whole square. So no matter where you fall in this sample space, you're guaranteed to fall in some B somewhere. Okay, so given that we have those B's, they're disjoint and exhaustive, for any event A, we can write that the probability of A is just the sum of their intersections with B, which makes sense, right? Because, so this is saying that the probability of A, the probability of being in this blue circle, is just the sum of the probabilities of falling into each of their individual intersections. Okay. Now, using the multiplication law of probability, which we saw on a previous slide, and you can also reference your sheet if you need, that is the probability of the intersection is equal to the conditional probability times the probability of whatever you're conditioning on. So all I'm doing here is for demonstration purposes, transferring this probability of A1, A intersect B1 is now equal to the probability of A given B1 times the probability of B1. I'm just using the formula to translate all these down. Okay, so now I can rewrite the probability of A is equal to the sum of the product of the conditional probabilities times whatever you're conditioning on. And this is just the law of total probability. We can also use this to get Bayes' theorem. So again, given that our B events are disjoint and exhaustive, we have this already. Probability, the conditional probability of Bj given A equals their intersection divided by A. Now what we can do is use the previous results. We can convert this intersection to a conditional times what we're conditioning on over, and then this is transferring this probability of A to the sum, which we got from the law of total probability. So a lot of these formulas are giving you the same things, or you're solving for similar things. But the reason that we have so many of them is because sometimes we only have limited pieces of information. So you might want to know this conditional probability, but you don't know what the probability of the intersection is. But you do know these pieces of information. So having all of these different formulas is helpful based on whatever information you have. You can hopefully calculate the probability that you need. Okay, so now we're going to go through an example practicing calculating these probabilities. We're going to use the HIV test status and the actual HIV status. So in this experiment, our sample space can be defined as this. H positive, T positive means you are actually positive and you tested positive. The double negative means you're actually negative and you tested negative. This H positive test negative, that is a false negative. The test is saying you're negative, but you actually have HIV. And H negative, T positive, that is a false positive. You are testing positive, but you don't actually have HIV. Okay, so given that this is our sample space, we want to obtain these probabilities based on the subjects in our sample. So I also first want to go over this two-way table a little bit. Here, these are the observed probabilities of individuals in each group. You might also see this table written as counts. So for example, this might be 10, 1, 4, and 85 out of a total of 100 subjects. So when you get the probabilities, you're sort of just skipping a step and you don't have to divide to get the percentages in each table. Okay, so let's think about what this cell here, this cell H plus T plus, with this 0.10 means. So this is, there are 10% of individuals in our study who are HIV positive and tested positive. So for this one, this is actually just our intersection. The intersection of H plus and T plus is 0.10. Okay. I'm going to give you a couple minutes to try these three. If you can't figure out the probability, I would at least try and use your formula sheet to write out what the formula would be and what you should plug in to obtain these. Okay, so I'm just going to start with this first one, the probability of H plus. So this is in our sample, what's the probability of having HIV, regardless of your test status? So that can be written using our law of total probability as the intersection of HIV positive and testing positive, and HIV positive and testing negative. And so as I said, all of these cells represent the intersections of all of these different things. So we can just grab these two. H positive, T positive is 0.1, and H positive, T negative is 0.01, so 11%. So the probability of having HIV based on those in our sample is 11%. Now we can do the same thing with a positive test. So probability of a positive test is going to be the probability of a positive test and HIV positive, and the probability of a positive test and HIV negative. So we grab these two intersections and add them up, and we get 14%. Okay. The next one is the probability of the union of HIV positive and testing positive. So probability of having HIV or testing positive. So using the probability of a union, we can write out this formula. It's going to be probability of H positive plus probability of T positive, again, minus their intersection, because in this case, we're adding that overlap twice. I have a question. Does anyone think that these two events, H positive and T positive, are mutually exclusive? So the answer is no, they're not mutually exclusive. And the way that you know that is because being mutually exclusive means your intersection is equal to 0. So this intersection, we can actually look right up here, and their intersection is 0.1. So they're not mutually exclusive. So there is some overlap between those two. Okay. So if we calculate that out, we'll have these probabilities. Okay. Using the same example, let's calculate conditional probabilities. So I'll give you a minute to just look at those, or maybe try writing out the formulas, and then we'll go over them. Okay, so the first one, this is read as the probability of having HIV given that you've tested positive. So this, just based on our formula of conditional probability, this is going to be their intersection divided by the probability of what you're conditioning on. So you're conditioning on a positive test. So we figured out all of these numbers on the previous slide. You can plug those in, you get 71%. We can do the same thing with the second one, the probability of being HIV negative, given that you've tested positive. So using the formula, it is their intersection divided by what you're conditioning on, and you get 29%. But you can also use the complement formula as well. 1 minus the probability of being HIV positive, given you've tested positive. You can use this because within testing positive, you know that if you test positive, there are only 2 options. You do or don't have HIV. So that's exhaustive. Those add up to 1. So you can use this complement rule. The same formula applies to this one. And so you get 91%. 91% of those who test positive actually do have HIV. This shows you that this is a fairly good test, and you can trust it, their results. Okay, so we've kind of gone over this in this last example, but I'm also going to try and introduce some new vocabulary to you as well. So diagnostic test statistics. Here, we have collected the following data on 200 subjects. In this one, I've given you the counts rather than the percentages. So to figure out the numbers that would go in these squares, you would just divide them all by 200, which is your total sample here. So when you give a patient a diagnostic test, you want to understand how good it is and how well you can trust its results. So you would like to understand how good is the test at identifying those with and without the disease, which means how good is it at putting people into this box, disease and test positive, and this box, non-disease and testing negative. We also want to know what is the probability that a patient actually has the disease given a negative test result, and what's the probability that the patient has the disease given a positive test result. So keeping this data in mind, I just wanted to show you how you might visualize this, going back to our Venn diagrams. So 16 subjects fall into tested positive, diagnosed positive. 9 fall into tested positive, diagnosed negative. 4 test positive, diagnosed positive, and 171 in the test negative, diagnosed negative. Okay, so how do we answer these questions? Question 1, how accurately does the test classify subjects as diseased or not diseased? So this is our true positive rate. So does anyone have an idea of how, using our probability notation, we might write that out? What probability are we looking for? We're looking for P, the probability of a true positive. So this is the probability that we've tested positive given that we have a disease positive. Right. This is a true positive. It's also called sensitivity. Again, we can use our formula to write this out. Because we don't have the percentages, we just have to calculate them out, as I said. So the probability of their intersection, 16 out of 200, that's right here. And then 20 out of 200, that's everyone that falls under disease. 20 out of a total of 200. So that gives us 0.8 or 80%. Now, we can interpret that as, of those who the test classifies as disease, 80% do actually have that disease. Okay, question 1 again, but another way of answering this, another statistic that we can get to answer that question, a false negative. So this means that the test told us that we don't have the disease, the test was negative. However, we know that the person actually does have the disease. So this is the probability of T minus given D plus. And we can get the same results here. Of those who the test classifies as disease, 20% do not have the disease. The same thing here, but we have our true negative, which is also referred to as specificity. We can plug in these same numbers. Of those who the test classifies as not diseased, 95 do not actually have the disease. And then we can do the exact same thing with false positive. Now, question 2, what is the probability of disease given that you've tested positive? So if a patient gets a positive test result, what's the probability that they actually do have this disease? So probability of disease positive given that your test is positive. We can again plug in these numbers in the same way. There's a 64% chance that the patient has the disease given a positive test result. And we also call this statistic the positive predictive value. And lastly, question 3, what is the probability of not having the disease given a negative test result? And it's the same thing here. 98% chance that the patient does not have the disease given a negative test result. So this sort of tells you that if your patient tests negative, there's a pretty good chance that you can trust that result and that they most likely do not have the disease. So how do we interpret these numbers that we just got about this diagnostic test? So the test is very specific for the disease. So the false positive rate is low. It's good at classifying not having the disease. The test is not very sensitive to the presence of the disease, so the false negative rate is high. So we get a lot of false negatives. It's not really sure how to detect whether or not someone does have the disease, but it's better at detecting whether or not someone does not have the disease. And maybe based on what disease you're looking at and what the treatment for that is, having a high specificity or a high sensitivity is more important. If the treatment is harmful, you really want to make sure, or potentially harmful, you really want to make sure that the person does have that disease before giving them the treatment. So depending on what's important to you, you may consider using a test with higher sensitivity if identifying disease is a priority, or vice versa. But you often have to choose what's more important to you because sensitivity and specificity are inversely related. Okay, so now we're going to go back to that Monty Hall problem using our probability theory. Let's see what we've learned in the formulas that I've shown you. Hopefully your sheet will be helpful here to come up with the same conclusion that we did at the beginning, which is the probability of switching doors and winning is 2/3, whereas the probability of not switching and winning is only 1/3. So we're gonna let W be the event that door 1 has the prize behind it, and that you're choosing door 1. And let E be the event that an empty door is opened. Okay. So given that we have chosen door 1, we want to know the probability of winning given an empty door is open. So this is the probability of W given E. So I will give you a second to try and write out just the formula for this. What is the probability of winning with the prize behind door 1, given that an empty door is open? Okay. So we can rewrite this using Bayes' theorem with this. So this, I've just used the definition of Bayes, which is on the back sheet. So we switch the order of the conditional and then multiply what we're conditioning on. And then on the bottom, it's the probability of E, which is using the law of total probability, the sum of both of these. So, but now how do we actually calculate these? What numbers go into here? So again, let's remember, starting up here, W is the event that door 1 has the prize behind it. And we're keeping in the back of our mind that we've chosen door 1. So what we're really calculating here is the probability of winning, sticking with door 1, because that's where the prize is, given that the host has opened up an empty door. So what's the probability of W? Well, W, just the event that the door 1 has a prize behind it, is 1/3. W complement, the probability that door 1 does not have the prize behind it, is 2/3. There's a 2/3 chance that the prize is behind some other door. Okay. The probability of E given W, the probability that an empty door is opened given the prize is behind door 1. Well, that's just guaranteed. We know based on how this game works that they are always going to open an empty door. Okay. And again, the same thing, probability that an empty door is opened given that the prize is behind one of the other two doors. Again, it's 1. That's just how the game is set up. Okay? So then we can use these numbers. We can plug them into here. And through these calculations, let me know if you have any questions, but I'm just plugging these numbers here into here. And I get this, simplifying because we're just multiplying each by 1. And then this gives us 1/3. So in the first example, we had the probability of switching and winning is 2/3. This is just sort of showing us the opposite, which is the probability of winning with door 1, not switching, is 1/3. Okay, so in summary, we went over how to calculate the probability of an event very simply, which is just the ways that an event can occur out of the total number of possible outcomes. We went over some set theory and set notation with unions, intersections, and complements, and then also how to calculate the probability of those things. We went over some formulas for conditional probability and total probability through the law of total probability and Bayes' theorem. We talked about independent and mutually exclusive events, and we spoke about sensitivity, specificity, PPV and NPV, which are your positive predictive value and your negative predictive value, to understand diagnostic tests. And that is all I have. Does anyone have any questions? So thank you for attending. We have, I think, paper copies of an evaluation.
Yep.
We have paper copies of an evaluation, so if you could fill those out, that would be great. And then on Zoom, we will be emailing you the evaluation. Thank you. What? I was going to say, is it this one? Stop share. Hold on 1 second.
No, that's fine, that's fine. So that's another
Just to make sure we see
right,
it.
right?
Yeah. So the one on sample size is part